Question two then is the question with just sort of using iterative formulas and things like that. So the first one is actually, I think, the first time we've seen something slightly different to the standard. So we've got the function y equals x to the x, and we're saying that this line intersects y equals 5. Okay, that's at a single point where x is equal to alpha, and we're asked to show that alpha lies between 2 and 3. Now I'm going to show you the way in which the mark scheme asks you to do it, but if you did something slightly different, slightly more standard, you can still recover and get your 2 marks. So because this is in this form, we can actually say, well, x to the x is equal to 5. So therefore the function that we're going to be substituting our 2 and our 3 into is x to the x minus 5. Okay, so that's our function that we are going to substitute into. So we're going to do f of 2, which is going to give us 2 to the 2 minus 5, and we're going to do f of 3, which is going to give us 3 to the 3 minus 5. So 2 to the 2 is 4, minus 5 is minus 1, 3 to the 3 is 27, minus 5 is 22. And then we can say here, well, as always, change of sign, therefore alpha lies between 2 and 3. So that's method 1, okay, creating the function of that intersection. The other thing which you could do, and this is how I approached this problem first time I did it. So I'm just going to remove the workings down here, and we'll look at a second method for solving this problem. So instead of that, I kind of ignored the second bit, the equals 5 bit. So instead, I just substituted 2 and 3 into the function. So I did y equals 2 to the 2 and y equals 2 to the 3. So then I got 5 and I got 27. Sorry, 4 and 27. And obviously there is no change of sign there. However, what we can say with this one is that 5 lies between them. 5 lies between 4 and 27, and therefore the point alpha must lie between them. So it's between that line, and the mark scheme allows this as a solution as long as it is completed with the therefore. The root is between 2 and 3. So it's better the first way I showed you, but this still recovers to give you 2 marks if you went about it in this way. So 2b is asking us to rearrange x equals e to, sorry, it's not at all. It's asking us to rearrange x to the x equals 5 into the form x equals e to the ln x over x. So what we first need to do is not have it x to the power of x. So if we take logs of both sides or lns of both sides, we're going to get the ln 5 bit, which we're after. And then I'm going to use the third law of logs to release that power down to the front here. So I've got x ln x equals ln 5. Now looking at where we're trying to get to, we want ln x over x. And I can do that at this stage by dividing by x. So I end up with ln x equals ln 5 divided by x. And then I finally want to get x on its own. So if I take e's of both sides, I'm going to have e to the ln x equals e to the ln 5 over x. And then we know that e and ln are cancelling each other out, leaving me with x equals e to the ln x over x, sorry, ln 5 over x, which was what we were looking to do for our 3 marks there. So for part C, we're doing the iterative formula. for a function, so that's why the calculator's here now. So we're saying that the next term, x n plus 1, is equal to e to the ln 5 over whatever the previous term was, x to the n. So we're told that x to the 1 is equal to 2. So we're going to use our calculator to actually do all of this for us. So the first thing we do is we store the 2 as the answer function, okay? And then we're going to set it up so we've got e to the power of ln 5 over, in the first case, the 2. So then when we press return, it's going to give us x2. So x2, and just having a look at what it wants it to 3 decimal places. So make sure that you do that. So if you miss out a decimal place, you will drop marks. So it's going to be 2, 3, 6. Now what's stored in answer is 2.23606, blah, blah, blah. So we just need to press equals again. And that gives us x3. So it's a really simple way of doing these iterative formulas. So we stored the 2 as ans and then pressed return twice. This case, we just got to make sure that we have rounded that correctly to 3 decimal places. So a really simple, quick question to go through, and if you use your calculator properly, you are really quickly going through those marks. So question part D, is the Simpson's rule question. So I've just highlighted the Simpson's rule there in yellow for you from the formula book. So whether we're doing Simpson's rule or mid-ordinate rule, first thing to do is to find h. So h is calculated by doing b minus a, which is 1.7 minus 0.6, divided by the number of strips, which in this case is 6. So we're just going to pop that straight into our calculator to find the value of h. So that's over 6. Sorry, I've not used the right one there. 0.5 that should be, shouldn't it? The second one there. So that comes to a fifth, which is 0.2. So h is equal to 0.2. So what that tells me, I'm using 7 ordinates, so I'm going to have x0 all the way up to x6 for my 7 ordinates. So 3, 4, 5 and 6, giving me my 7 numbers. So my first one is 0.5. My second one is 0.2 more, so 0.7, 0.9, 1.1, 1.3, 1.5 and 1.7. And you'll notice that that does match with the upper limit, so I know that I am on the right lines here. The next thing I need to do is find my y values. So I will show you the first one and then I'll populate them off screen, so you don't need to worry about watching me typing numbers into a calculator. So the first y value is found by doing this function. Don't try and integrate it or anything like that. We're just going to put the x0 value into this function. So 5 minus 0.5 to the power of 0.5. And that's going to give me my first value. Now I'm asked the answer in 3 significant figures, so I just need to make sure I'm working to more than that in the question, so that when I do my final answer, I've got a better approximation. So 29, let's go 29 again. So let's work to 5 significant figures here to then round our final answer. So I'm just going to populate all those numbers now, and then the video will resume with these populated for us. So there are all of the y values there populated. Obviously, if you're watching this video, it's worth just making sure you know where all of those came from and you are able to calculate those yourself, because in your exam you will not have the beauty of it just appearing on the screen. So then we need to actually apply Simpson's rule to this. So Simpson's rule, taken from the formula book, is 1/3 times h, so in this case 1/3 times 0.2, and then big curly bracket for the first and the last. So the first and the last is going to be 4.2929 plus the last one 2.5353. We're then adding 4 lots of all of the even numbered y ordinates. So the even numbered y ordinates. So it's going to be this one, and this one. Okay, so 4 lots of the evens. So we're going to then have plus 4 lots of 4.2209, 3.8895, and 3.1629. Now, obviously, in your exam, you might be thinking, oh, I'm time pressured. I want to not write all this down. If you don't write this step down, you will not get more than 2 marks if you make a slip. If you don't make a slip, then absolutely brilliant. You get the right answer, you're fine. But if you do make one mistake on any of these numbers that you're typing into your calculator, and you haven't written this step down, you've capped yourself at half marks for this question. So just carrying on then it's 2 lots of all of the evens. So the evens are the 2 and the 4. We've already used y0 and yn, so it's all of the other terms there. So it's 2 lots of the ones I've done in purple, so 4.0905 plus 3.5935. And then it's a case of plugging this whole thing into your calculator. And I am just going to take my time and just show you exactly how I would do this. So it's going to be 0.2 over the 3, a third of 0.2. I'm going to open one bracket, which is the big curly bracket, and then I'm going to open the second bracket. Okay, and it's really important that you do show your brackets, or you do use brackets like this. If you just opened up one bracket, you will get the wrong answer out of your calculator because of the way in which it will follow the rules of BIDMAS. So 5353. That closes off the first bracket. So I'm copying exactly as it looks in the question. And if you do this, you will not make an error. Okay? If you try and be a bit too clever or try and do it too quickly and not follow the brackets that we've written out really clearly, then you'll be fine. So close that bracket off and finally add 2 lots of the final 2. Okay, and once you've done that, close off the 2 brackets. So that one closes off the things I'm multiplying by 2, and that one closes off the big curly bracket. Press return, and then we get our solution, and we want to give that to 3 significant figures. Now what you can do is write it down as it is, just to show your examiner where you are, and then round that to 3 significant figures. So 4.49 to 3SF is absolutely fine and gives us our 4 marks. So quite a lot of process there, but nothing too taxing mathematically. So it is just really important that you show your workings really clearly, so it's really obvious, and then you get your 4 marks, no problem at all. Now part 2 then says, hence do an approximation just for 5 to the x, not 5 minus 5 to the x. So I'm just going to keep this number here, but I'm going to just remove all the workings and show you how we go about part 2. Okay, so the temptation with part 2 is to just do 5 minus this number and get the solution. But that's not quite right, because what we're doing is we're doing an approximation for the integral of 0.5 1.7 without the 5 and the minus 3x. So if you were doing this question, you would actually do this as 2 separate integrals. Well, not quite, you wouldn't necessarily write it like this, but this is what you're doing. You're integrating 5 between your limits, and then you're subtracting the integral of x to the x between your limits. So what we know this part, we know the second part. That integration is estimated by your solution here. But what we still need to do is this first integration. So we're integrating x with respect to x, which is going to give us, sorry, we're integrating 5 with respect to x, which is going to give us 5x between our 2 limits, 0.5 and 1.7. Okay, so when we then do that, we're going to do 5 lots of 1.7, subtract away 5 lots of 0.5. So we actually find that that comes to 6. So our estimation here is actually 6 more than the integration for x to the x. So when we are estimating x to the x, we need to do 6 minus the 4.49. Sorry, 6 minus 4.49 to give us 1.51, which is the correct solution to the approximation. Because when we actually integrated this first thing, we were including this 6 more that we didn't actually need.